Hi, my name is Truong-Vinh Hoang, and in this video, I want to summarize our work on machine learning-based conditional mean filter for nonlinear data assimilation. Nowadays, data assimilations, in particular filtering, has many applications ranging from weather and environmental forecast to digital twins. The filtering problems usually decreased by two equations. The first equation involves the evaluation of the about nonlinear dynamical systems, and the second equation is a model of the observation that we obtain at a certain discrete times. Filtering aim to predict the state of the dynamical system, which is unknown based on the observations. To do so is have two steps. The first step is forecast, in which we use the dynamical system to forecast the state at the time that we will have the observation data. And in the update step, when we actually have access to the measurement data, we update the forecast random variable, and the obtained updated random variable has less uncertainty about the state of the dynamical system. Ensemble Kalman filters is a popular method for filtering, and is based on linear updating map. Thanks to the simplicity of the linear updating map, ensemble Kalman filter is very easy to implement it and has a very good performance for linear Gaussian setting. However, for nonlinear Gaussian setting, the performance diminishes. So this is the motivation to develop nonlinear filtering methods. In the work of Lai and Becker, which is given here at the second reference, they propose a conditional mean filter based on conditional mean. The conditional mean is defined as a composed map phi and apply on the forecast of observation. And the conditional mean has a certain values of certain vector y is equal to the posterior means of the Bayesian posterior given observation data equal to y. And the conditional means is given by equation phi, which is equal to the forecast random variable plus the difference between conditional mean applied at actual measurement data minus the conditional mean applies on the measurement random variable. So Lai and Beck show that the conditional mean filter is identical to the EnKF for linear Gaussian setting. Moreover, the updated random variable predict correctly the posterior mean value thanks to the use of conditional mean in the filter. We further show that actually the variance of the updated random variables is identical to expected conditional variance. So to show this property, we use a simple statics inverse problem, in which the posterior means with given in figure 1 for different values of observation. As we can see, that is strongly nonlinear. However, when we use ensemble Kalman filter, the means of the updated ensembles is linear with respect to the observation, and we can see that there are significant bias in terms of the mean, and we can verify this fact by looking at the figure 2, in which I show the comparison of the PDFs of ensemble Kalman filter, the conditional mean filter, and Bayesian posterior. So between Bayesian posterior and our filter, which is in blue curve, they have identical mean value. While the mean value of the EnKFs is significant bias compared to the Bayesian posterior mean. In terms of variance, the conditional mean filter variance is constant. However, it corresponds to the expected conditional variance, while the variance of the EnKF is also constant, but it has significant error compared to the conditional variance. So in general, conditional mean filter does not predict 100% correct the PDF of Bayesian posterior. However, it can predict exactly the posterior mean, and compared to the EnKF, the variance of conditional mean filter error is significantly smaller. Yeah. So the next step is how to implement the conditional mean filter. In the paper of Lai and Becker, they use the likelihood approach. Here in our paper, we propose to use neural network based on the orthogonal projection properties of the conditional mean. So actually, we approximate the conditional means map files as a combination of linear maps, which we can obtain from EnKF, and nonlinear map, which can be an ANN. And then we use orthogonal projection to identify the hyperparameter of the GNN of the ANN. Sorry. In section 3.1, I showed the summarize of the algorithm for machine learning based conditional mean filter. So it still has two steps, forecast and update, in which the forecast steps is identical to that of EnKF. In update step, when we have sample of the forecast random variable, then we use these ensembles to train our neural network, and in turn obtain the conditional expectation map. Then we evaluate the ensemble of the conditional mean filter updated random variable. We examine the performance of machine learning ensemble conditional mean filter for tracking the Lorenz-96 and Lorenz-63 systems. in comparison with the EnKF, as well as the likelihood approach for implementing the ensemble conditional mean filter. Compared to the EnKF, our filters consistently outperform, thanks to the non-linearities of the updating map. Compared to the likelihood ensemble conditional mean filter, our machine learning ensemble conditional mean filter has similar performance for large ensemble size. However, when we have small ensemble size, our machine learning based approach outperform. And actually, for some small ensemble size likelihood ensemble conditional mean filter, even so, a reduced performance compared to the EnKF. And that's this trend we observe not only for Lorenz-63, but also for the Lorenz-96 systems. So in conclusion, we developed a machine learning ensemble conditional mean filter. We saw that the ensemble conditional mean filter not only correctly predict the means of the posterior, but also predict correctly the expected conditional variance. We applied our methods in tracking the Lorenz-63 and Lorenz-96 systems, and we saw that our methods consistently outperform the EnKF. And actually, by using machine learning based approach, our methods outperform the likelihood based approach. These results we reported in the first reference I give you here. With that, I thanks for your attention, and I looking forward for in-person discussions on our poster. Thank you very much.